So we have completed chapter 1, and the last lesson in chapter 1, we looked at developing the idea of the instantaneous rate of change based on the average rate of change. We developed it by looking at the distance h between the two x values when you're looking at the average rate of change. When we look at that distance between the two x values and we take the limit as h approaches 0, those two x values close in, so there's not as much distance between them. And then it gets closer and closer to 0, which then we get close enough where we can say it's an instantaneous rate of change. Now in chapter 2, we are going to start focusing on the idea of the derivative. This is the first major branch of calculus. Everything we've done up to this point is building it up so that we can start talking about the derivative. Now we're at the point where we're going to make the connection between the instantaneous rate of change and the derivative. We're going to also look at the basic derivative rules and then how to interpret an answer when we're talking about a derivative in the context of some real-world problem. In the previous section that we talked about, we looked at this right here, which was the limit as h approaches 0 of the difference quotient. That is actually the derivative definition. This notation right here, it looks like the function f of x, but it has the little prime symbol there. That means the derivative of the function f. So the instantaneous rate of change is the derivative. Now, when we look at this, we can look at it as two different ways. We can look at the derivative as the slope of the tangent line to f of x, but we can also look at it as the instantaneous rate of change of f with respect to x, so specifically at a point. So let's look at our first example. It says find the derivative of the function f of x is equal to 5x plus 8. Now right away we see that this function is a line. It's a linear function. And when we talk about linear functions, we know that no matter what point we pick on that line, or no matter what 2 points we pick on that line, if we're looking at an average rate of change, the slope will always be the same because the slope of a linear function is constant. So without doing any work, I should know that my answer is going to be 5 because this is linear and 5 is the slope here. But working through it using our limit definition of the derivative, we have the limit as h approaches 0, and here's my difference quotient. So now I got to find f of x plus h. So everywhere in my function that I see x, I'm going to replace it with x plus h. So that's right here. So I have 5 times what used to be x, and then I add 8, and that x plus h goes in where x used to be. And then I'm going to subtract fx plus 8. Don't forget that you have to distribute that minus to all the terms in the function. When we distribute and expand everything, this is what we have here. And then that's where things start to drop out. I have a plus 5x and a minus 5x, and I have a plus 8 and a minus 8. So after I start adding everything up and things drop out, I'm left with 5h over h. And then the h's drop out. So now if I take the limit as h goes to 0, I'm just going to get 5. So we would interpret this by saying the instantaneous rate of change of the function 5x plus 8 with respect to x is a constant 5 everywhere, which we should expect because the original function is linear. So now let's look at the notation that we use for the derivative of a function. We have multiple notations for this. We have what's called prime notation. Then we would use this symbol here that looks like a little dash up in where we normally would see an exponent, and we would say f prime. So if we're taking the derivative of f with respect to x, this is one of our notations. We call it f prime. The same thing goes for y. If we have our equation set up with y equals, and then you have your equation with respect to x, then when we take the derivative, we would call that y prime. This notation here, and forgive me because this word is a tongue twister for me. This notation here was developed by a guy named Leibniz. And so this is stating the same idea. It's just written in different notation. You would state this as dy dx. And this is the same thing here. In this case, I would say the derivative of f with respect to x. So we would say df dx. And then this notation here, it's the same idea again. You're just stating here first that you're taking the derivative with respect to x in general, and then after that you state the function that you're taking the derivative of. So you would say the derivative with respect to x of the function f. So these are all different ways that we can state the derivative with notation. So let's start looking at some more examples here. So we have f of x is equal to x squared plus 6x minus 2, and we need to find each of the following values and interpret the result. So for part A here, notice there's no prime. Okay, so we are literally just evaluating the function at x equals 5, which means I'm going to put 5 in for x and evaluate it. So the point of this example is to be able to tell using our notation when we're taking the derivative and when we're not. So this is definitely not taking the derivative because we don't have the prime. This is just plugging in 5 into the function. This one here, because it has a prime, that means we're taking the derivative with respect to x. This one here, not only are we taking the derivative, because I can see that I have the f prime there, but this is also stating find the derivative and then evaluate it at x equals 5. So there's a big difference between evaluating the function and then evaluating the derivative. So when we look at how to actually work it out, when we plug in 5 into our function, we get 53. Let's look at the next one. When we want to find the derivative, we're going to take the limit as h goes to 0 of f of x plus h minus f of x over h. So I'm going to plug in, to find the f of x plus h, I'm going to plug in x plus h everywhere I see x. So that's this right here. You can see that the author of the book labeled it. So this was x squared, this was 6x, but now we're replacing the x with x plus h, and then we have the minus 2 for the constant. Then we have to subtract our f of x, that's this. And then we go through the process of cleaning it up, and a lot of things should cancel. And then at the end, we can factor out an h, and what we're left with is 2x plus h plus 6. And then now, because we've got rid of the h in the denominator, we can use direct substitution to find the limit. In this case here, when we plug in h is 0, we're left with 2x plus 6. So this is the derivative with respect to x, and look how we have the notation here. This tells us at any given x on that function what the instantaneous rate of change would be. So for example, if I wanted to find the instantaneous rate at x equals 0, I would have 2 times 0 plus 6, so that would give me 6. Now the last part is to not only take the derivative, but to evaluate it at 5. We already found the derivative. The derivative was 2x plus 6. Now if we evaluate it at 5, I just have to plug in 5 for x, and we get 16. So 16 is the instantaneous rate of change on the function at x equals 5. So now for the rest of the lesson, you'll probably appreciate this. We are going to go through rules of derivatives, and these are basically shortcuts to using the limit definition. When we calculate the limit using the limit as h goes to 0, that definition, it can be very long, very tedious, and it's easy to make a mistake because a lot of them are pretty lengthy. So these rules are shortcuts to using that limit definition. So someone took the time to prove these rules work So then we have the privilege of using them. So we're going to go through those rules. Okay, so the first rule is about the derivative of a constant. So if we just have a horizontal line, y equals 7 or y equals 50, and that function is just a constant, just some number because we're looking at a horizontal line, then when we take the derivative is 0. And when you think about it, it makes sense because if we have a horizontal line and we look at any point on that function, the instantaneous rate of change is going to be 0 because the slope on that line is 0. There's no tilt. So no matter what point I pick on that constant function, the slope is 0. So here's an example on how we can use it. Here are two functions we differentiate using our first rule. We have the function f of x is equal to 4. Because that's just a constant 4, then without even really doing any work, we can just say the derivative is 0. And the same thing for this. We have f of x is equal to negative 16. This is a constant. So I know that the derivative, no matter what point we look at, is going to be 0. So in this case, they're saying not only find the derivative, but then evaluate it at x equals 2. Because I know that's a constant function, it doesn't matter what point I pick, the derivative is going to be 0 without doing any work. I can just say that the derivative at 2 is 0. The next rule is used for when we have x raised to some power. So when we have something in this form, x to the n, without having to go through that limit definition, we can just say that the derivative of y with respect to x is n times x to the n minus 1. So when you look at this, really what you're doing is you're taking the n and bringing it down, and that becomes your coefficient of x. And then your exponent is decreased by 1. So if we have x squared, then the derivative is going to be 2x to the first, because this exponent becomes the coefficient of x, and then you decrease the exponent by 1. So that's why we have 2 to the x, or sorry, that's why we have 2x to the first. The second part, we have f of x is equal to x to the fifth. So to use the power rule for derivatives, that means this 5 is going to come down in front as the coefficient, and then the 5 is decreased by 1. So our derivative would be 5x to the fourth. So now in this part C, we have y is equal to x. This might seem a little bit unusual, but when you think about your rules of exponents, it will make sense. So my exponent here is 1. Even though we don't write it in there, we know that if we just have an x, that's x to the first. So we bring down that 1 in front, but then we have to decrease that exponent by 1. So then we have x to the 0 because we take 1 minus 1. And as long as x itself is not 0, then this expression here is 1, right? Anything raised to the 0 power, with the exception of 0, is 1. So here's our rule that if we just have y is equal to x, using the power rule, we have that the derivative is just 1. So this is kind of like a special case of the power rule. Okay, let's look at example 5. We have f of x is equal to the cubed root of x squared. I suggest, because it makes it so much easier, when you're taking the derivative of a function that involves any kind of root, rewrite that in exponential form, because then you can use the power rule. So for the first part, we're going to evaluate the function at x is equal to 8. So I'm going to take 8 and plug it in. So I have 8 squared is 64. And then I'm going to take the cubed root of 64, and that gives me 4. So there's the explanation there. Although I did it in reverse direction, I squared it first, but that order doesn't matter which you do it. And then when we want to find the derivative of this, remember when you have roots, you can rewrite it where the root is in the denominator in the exponent. So this would be rewritten as x to the 2/3. So 2 up in the numerator of the fraction means it's x squared. The 3 in the denominator tells you the root. So this is the third root. So now that we've rewritten this function using exponents, we can apply the power rule. So when I take the derivative, this 2/3 comes down in front as the coefficient of x, so there we go. And then I have to subtract 1 from the exponent. When I subtract 1 from 2/3, I'm going to get a negative number. And then if I take 2/3 minus 1, that's going to give me negative 1/3. So I have 2/3 x raised to the power of negative 1/3. If you don't like using negative exponents, remember using the rule of exponents wherever the negative exponent is. So if you have x to a negative exponent in the numerator, then you can bring it in the denominator to make it positive, and vice versa. If your negative exponent is in the denominator, then you can bring it upstairs into the numerator and make it positive. So this is technically in the numerator, although we don't show the fraction bar with a 1 underneath it, but we know that this x to the negative 1/3 is in the numerator. So to make that negative 1/3 positive, we're going to put that in the denominator. One thing to be careful of, because I see a lot of students do this, the 2 does not have a negative exponent. I see a lot of people look at 2x to the negative 2/3 and they want to flip the 2 also, but the 2 is not being raised to a negative exponent. So the 2 stays in the numerator. So be careful of that. Only flip the factor that has a negative exponent. Okay, now part B is asking not only to find the derivative, but then to evaluate it at 8. So now that we have our derivative, which is 2 over 3x to the 1/3, I'm going to plug in 8. So I have in the denominator 8 to the 1/3. That's going to be 2 because the cubed root of 8 is 2. Then I have 2 times 3 is 6. So now I have 2 over 6, and we can reduce it to 1/3. Okay, the next example, we have f of x is equal to 1 over x to the 4th. We want to find the derivative, and then we want to find the equation of the tangent line. And we want to look for that tangent line at the point negative 1, 1. So when we rewrite, here it is right here, when we rewrite that function as x to the negative 4, now we can use the power rule. So the negative 4 comes down in front as the coefficient, and then we decrease the exponent by 1. So then in the exponent, I would have a negative 5 because I would take negative 4 and subtract 1. And then when we rewrite it without negative exponents, then we can just put that part back downstairs again with the negative exponent. I personally don't care if you leave it like this. However, you might want to pay attention to what the homework asks for when you enter the answer. The program might not be as flexible. So just make sure if it says next to the answer box, write your answer with positive exponents, that you need to take that extra step to rewrite this. Okay, so now we have the derivative. Now remember, the derivative represents the instantaneous rate of change at any point on that function. We would just have to plug in that value of x. And that instantaneous rate of change is the slope of the tangent line. So we have all the pieces we need to come up with the line that hits that point at negative 1, 1. So here's our x value. So if we want to find the slope of the tangent line, we would use the instantaneous rate of change, or the derivative, and plug in the value of x that we want, that we're interested in. So I'm going to take negative 1 and plug it in here. And then when we do that, we're going to get positive 4. So this is telling me at x is equal to -1 on that function, the tangent line is going to have a slope at 4. Or you can say the instantaneous rate of change at x equals -1 is 4. So now that we have the slope, if we're using point slope form, the slope here is going to be 4. And now we just have to find a point to plug in that we know that's on the line to get our equation. We were given this point on the graph to find the tangent line. So we know that this point is part of the tangent line. So I'm going to use this as my x and this as my y to plug in to find the rest of the pieces for our tangent line. Now, one thing to mention, sometimes this y value is not given. Sometimes it just says find the tangent line at x equals -1. So if the y value is not given, you would have to take an extra step to plug in -1 into the function, not the derivative, into the function to find the corresponding y value. So we're going to let x1 be -1, y1 be 1, because we're using that point that was on the function to find our tangent line. So when we plug that into our point slope form, we get this. And then if you want to put it in slope intercept form, you just do a little bit of rearranging, and we get y is equal to 4x plus 5. When we graph 4x plus 5, remember what this is. This is the tangent line at x equals -1 on this function. So when we graph the function, this is our graph. And then when we look at the point -1, 1 on here, that's this point right here, and we draw the tangent line 4x plus 5, this is what it's going to look like. So here we have how to find a derivative if you have a constant times a function. So if I have a constant times a function, when I take the derivative, I can really just take the derivative of the function and then multiply it by c. So in other words, this c does not affect the derivative. So instead of taking the derivative of c times f of x, sometimes it's easier to take the derivative of f of x and then add that c back in by multiplying by c, whatever that constant is. So for example, we're going to look at this function now. So let's rewrite x to the 8th in the denominator as a negative exponent, and so we can bring it up and use the power rule. So when I rewrite this, I have 4x to the -8. Here we have an example of a constant times our function. So I have 4 times x to the -8. So I can find the derivative of x to the -8 and then multiply it by 4. So if I take the derivative, then I'm leaving the 4 in there. And so I'm going to take this -8 and bring it down in front using the power rule. So I have 4 times -8 now because the 8 gets pulled down in front. Then I have to subtract 1 from my exponent. So that gives me a -9 here. So when we clean this up, we are going to get -32 times x to the power of 9. Here is another variation of that idea. If I take the derivative of a constant times x, that is going to be the same thing as finding the derivative of x and then multiplying by c. And another way to look at it is if I have c to the x to the power of 1, the 1 comes down in front, so I'm left with 1 times c in front, and then I have to decrease that exponent, which is 1, by 1. So then I would have c times x to the 0, then we can say that x to the 0 is 1. Which means we have c times 1. So this is just a fancy way of saying if you take the derivative of c times x, the derivative is just going to be c. So looking at example 9 using that rule of c times x, we have y is equal to 8x, so this is our constant that's in front, our coefficient. So then using that rule, the derivative would just be 8. Same thing here. If we have a function negative 14x, our derivative would just be negative 14. Now, all of the rules up to this point that we have talked about are all variations or special cases of the power rule. Now we're going to look at the rule of what happens when we take the derivative of a sum or difference. So if I have two functions added or subtracted, then when I take the derivative, I can take the derivative of each one separately, and that's going to be the same answer as if I took the derivative of both of them together as a whole. In example 10, we're going to find the derivative of y with respect to x. And remember, this is that Leibniz notation, so this is pronounced dy dx. So if I have 5x to the third plus 4x squared plus 9x minus 7, think of each of these terms as a separate function. So think of this as a separate function, this as a separate function, the 9x and the minus 7 as separate functions. And we're just adding and subtracting them together. So when I take the derivative of this, I'm going to take the derivative of each term separately, and that will give me the derivative as a whole. So I'm going to take the derivative of the first term, which is 5 times x to the third. Using the power rule, I would have 3 that comes down in front. That would give me a 15. And then I decrease the exponent by 1. So this would be 15x squared. The derivative of this, I would take the 2 down in front. That would give me an 8. And then I decrease the exponent by 1. So that would give me 8x. This here is 9x. When we take the derivative of this, I bring the exponent down in front, so I would have 9 times 1. And then when I raise x to the 0 power, that would be 1. So now I'm left with 9 times 1, which is 9. And then here we have a constant, and so this is just going to be 0. So now when we clean that up and we drop out the 0 because we really don't need it, our derivative is going to be 15x squared plus 8x plus 9. So in this example 11, we are asked to use this function x squared minus 4x plus 3. We are asked to find the value of x so that when I plug in that value of x, I get out 0. And then in part B, we're asked to do the same thing but with the derivative. So we're going to find the derivative, set it equal to 0, and find the value of x that gives us the derivative is equal to 0. So looking at this first part, we're going to take the function and set it equal to 0 and solve for x. This works out very nicely where we can factor it and we can find that the value of x is 3 or 1. Since this is a quadratic, if it doesn't factor nicely, remember you have other methods. You have complete the square or you have quadratic formula. So when I plug in x is equal to 1 or 3 into the function, I'm going to get out y is 0. Now for the second part, we need to find the derivative and then set it equal to 0. So when we take the derivative using the power rule and we look at each term separately, we're going to get 2x minus 4. And now we're going to take that derivative because part B says find the value of x that makes the derivative 0. Now we're going to set that equal to 0. And when we solve that for x, we're going to get x is equal to 2. You will find that this concept of setting the derivative equal to 0 is going to pop up several times throughout the course. This is key to looking at your maximum and minimum values on the graph. Because when you look at a maximum or minimum, I should specifically say local max or min, that's going to be the top or the bottom of a hill or a valley. In this case, we're looking at something that's concave up, so we're going to have a minimum. And this is telling me the value in which that minimum occurs. Because remember what the derivative means. The derivative is going to give us the slope or the instantaneous rate of change at any point on that graph. So if I find when the instantaneous rate of change is 0, that's going to be at a horizontal line. That is telling me that the slope of the tangent line at x equals 2 is 0. So that gives me a minimum. In this case, there are times where it would be a maximum if it was concave down. So this idea of finding when the derivative is equal to 0 is going to tell us a lot about the graph. Looking at example 12, we have y is equal to 9 times the cubed root of x squared. This notation here is an extension of the Leibniz notation, and this is basically saying we're going to find the derivative dy dx, and this line with the x is equal to 8 here is another way to say, and then evaluate it at x equals 8. So this is just another way to say f prime of 8. Before, when we would use the prime notation for derivative, and then we had a number in here, that means find the derivative and then evaluate it at x equals 8. Okay, so my hint to you before, when you're dealing with radicals, you want to make sure before you take the derivative to put it in exponent form. So we're going to rewrite this function as 9 times x to the 2/3. So then, let's see, oh, here it is right here. It's written right here. And then we're going to take the derivative. So this 2/3 is going to come down in front with the 9, and you multiply the 9 and the 2/3 together. And then you have x raised to the power of, and then you take 2/3 minus 1. So that's going to give you a negative 1/3. So when we simplify this, 9 times 2/3 is 6. And then when I subtract 1 from the exponent, that's going to give me x to the negative 1/3. Then if we want to rewrite it with the negative gone, we need to flip x to the negative 1/3. So that's going to go downstairs as a positive. And this is an example of where I was saying that sometimes students forget and flip the 6 too. We're not going to write this as 1 over 6x to the 1/3. The 6 does not have an exponent that's negative. So the 6 stays in its original position. And then if we want, again, to write it differently, and we want to put it back in radical form, x to the 1/3 is the same thing as saying the cubed root of x. So any of these answers are fine by me. They all mean the same thing, but just make sure you read the directions in your homework so that you're writing it in the format that the program is expecting. So now we found the derivative, and the second part of this is we need to now evaluate it at x equals 8. So I'm going to plug in 8 here. So I'm going to have 6 over the cubed root of 8. The cubed root of 8 is 2. So then I have 6 over 2, which is equal to 3. So now we're going to talk about marginal change. And at first, I'm going to explain to you the general concept, and then we'll apply it to business. So marginal change shows how a small change, and we're going to be looking at it in terms of 1 unit, a small change in the independent variable and how that affects the change in the dependent variable. So if you're looking at a graph and you're looking at the x-axis and you move over 1 unit, so wherever you're sitting on the x-axis, you move over 1 unit, how does that affect the change of your y value or your dependent? So that's the general concept of marginal change. It's like looking at the effect of doing just a little bit more or a little bit less of something, but generally we're going to look at it if you're increasing by 1. So we're going to look at example 13. So we're going to look at it generically right now, and then I'll discuss how this applies to business. So it says if y is equal to 6x to the 4th, we want to find dy dx. So that's the derivative with respect to x. And then we want to evaluate it at x equals 3 and interpret the results. So when we take the derivative of 6x to the fourth, we can just use the power rule. So we're going to take the 4 down in front, and that's going to make it 24 in front. And then we decrease the exponent by 1, and that's going to give us 24x to the third. When we evaluate that at x is equal to 3, we're going to take 3 to the third, which is 27, and then multiply by 24, and we're going to get 648. So what this is saying is if we look at the function 6x to the fourth on a graph, and we're looking at the point x equals 3, the instantaneous rate of change is 648. And although we don't write it in there, we know that it's 648 over 1. So that means if I move my x value 1 unit to the right, so if I increase x by just 1, we can approximate the change of the function as 648. So this is just talking in general. Now this isn't going to be the exact value because when we're looking at the derivative, we're looking at the slope of the tangent line. And when we're looking at that exact point, x equals 3, that's just going to be the closest estimate we can get by using the tangent line, by going up 1 unit on that tangent line. So here's the official interpretation. If x increases by 1 unit in value, from x equals 3 to x equals 4, then the function will increase in value by approximately 648. Now, looking at this graph, we have a function that's being used to model a relationship, and we're going to look at the tangent line on the curve and notice that the tangent line at the point x equals 3 is pretty close to the function overall because this function, the square root of x, rises slowly. So the tangent line is going to be close to it, almost lays on top of it. So if I'm looking at x equals 3, and I use the tangent line to approximate what happens when I go to 3 to 4, I'm looking at the slope of the tangent line. So to go from 3 to 4, looking at the tangent line, I would find that it's 0.289 because I would find the derivative, that would give me the slope, and then plug in the slope at 3. So here's the change. So this would mean if I'm at 3 and I approximate the change using the tangent line and I go over 1 unit to x is equal to 4, my increase of the function should be approximately 0.289. Now, if we want to find the exact change, we would just plug those two values into the actual function of the square root of x and subtract them to see how it changes. Notice that these are pretty darn close. Our approximation is close to the actual change, and that's because the tangent line is super close to that curve of the function. So now let's look at what happens when the tangent line doesn't lie close to the curve. So here we have this function in red, and when we look at the tangent line at x equals 3, isn't super close to the function like it was with the square root of x in the previous picture. Notice that the function jumps up pretty fast and the tangent line goes off this way. If I make an estimate of the change at x equals 3, I'm going to get 648. If I look at the actual change by plugging in the difference between the value of 4 on the function and the value of 3, the actual change is 1050. That is a pretty big distance. So when you are finding marginal change, you want to keep that in mind. The marginal change is the way to make an approximation, where the exact change is going to be where you're plugging in those values on the function and finding the difference between the two. So now that we understand the idea, the general concept of marginal change, we can apply that to business by looking at the revenue function, cost function, profit function. If we, for example, are looking at a revenue function and we're looking at the graph, along the bottom, when you're looking at the x-axis, that is going to represent the number of items sold. And then on your y-axis, you're going to have the amount of revenue. So if I asked you to find the marginal revenue, or how much additional money we could make if we sell one more item, if we've already sold 100, then we would find the instantaneous rate of change at 100, and then use the slope of that tangent line to see what changes if we move up one more unit. So if we go from 100 to 101 products, how much more money we could make by just increasing that by one more product. And that same idea can apply to profit and cost as well. The last topic we're going to talk about in this lesson is conditions for when you can't take the derivative. There are special cases when you take the derivative and you're trying to evaluate it at a point where that value will not exist. And so there are some rules for that we can follow. So if you have a function that has a point of discontinuity, like this one right here, then when I try to take the derivative of f of x at that specific point A, I'm not going to get an answer. So the derivative of f of x at that point A does not exist. So here's a second example of when a derivative would not exist. When you have a graph with a corner like this, so for example, the absolute value of x, you are not going to have a derivative that exists at that point A where the corner is. And that is because the derivative is based on a limit, and in order for that limit to exist, meaning the derivative as well, the limit from the right and from the left have to be the same. So if I look at a corner piece in general, if I come across this way and I approach that point from the left, my tangent line is going to lie like this. If I come in from the right, my tangent line is going to come up this way. Now remember, the derivative is the slope of the tangent line at that point. Because I have two different tangent lines, depending on which way you're coming in at with the limit, you have two different slopes because of the two different tangent lines. And so it's not well defined. So that is why we do not have a derivative at corners. And one more example of where we would fail to have a derivative is when we have a tangent line that is vertical. That means when you have a vertical line, the slope is going to be undefined. Here are two examples where you would have a vertical line as the tangent line. It's when you have a cusp like this, because as I get closer and closer to the tip of that cusp, the tangent lines are getting more and more steep, and then it's going to end up being vertical right at that point of the cusp. Same thing here, where it turns from concave up to concave down. That is going to have a vertical asymptote as well, which means the slope is undefined, which means the derivative is undefined. Last example, I want to show you using technology, meaning we're going to use GeoGebra to calculate a derivative. So we're going to use this as our example. We're going to find the derivative of 90 t squared minus t cubed. So here is GeoGebra. I've created our function and defined it here in the first input. Now, if we want to find the derivative, we can use the command derivative. When we start typing, this will come up, and we want to come over here and we want to do the derivative of a function. I'm going to click on that. And then inside here, I can put the function. Now, you can either directly put in there what the function is and type in 90 t squared minus t cubed, or since we already defined it, I can just put in there f. When I hit enter, it will tell me what the derivative is. So looking at this, GeoGebra has put it in descending order. So GeoGebra calculated this first. If you take the 3 down in front, that gives you a negative 3t squared. That's this term right here. And then if you calculate this second, I take the 2 down in front, that gives me 180. and then that will leave me with t to the first because I decreased the exponent by 1. So when you do derivatives by hand, it's handy to be able to check and make sure you did it correctly. Also, you can evaluate now what the derivative is at a certain point. So if I want to calculate the derivative, for example, at t is equal to 50, I can type f, then put my little prime symbol, and then in parentheses, I would put 50. Then I would hit enter. So on the graph, f prime of 50 is 1500. So if I look at 50, somewhere in here, about right here at 50, the tangent line would come up like this, and that would mean that it's the instantaneous rate of change at 50, which means this would be the slope of the tangent line. Now for practice, I know I already showed you how to do this. Let's do this for practice. Let's find the tangent line. I'm going to start typing tangent. And I'm going to come over here and I'm going to do at a point with a function. My point that I want to use is 50. Now when it asks you for the point, it's not asking you for just the x value. You have to put in the x and the y. Also, because I don't know offhand what the corresponding y value is, I'm going to actually enter it in using function notation. So I'm going to say 50, comma, and then f of 50 for my y value. So here's the point that we're going to look for the tangent line. 50, comma, f of 50. And now I need to put in, whoops, I missed a parentheses. Now I'm going to put in the function that I want the tangent line on. And I define that as f, so I'm going to put in f, and I'm going to hit enter. So here's my tangent line. If we zoom in a little bit, here's that point right here, and then here's the tangent line in black. And it says that the tangent line at that point is 1500x plus 2500. And as you can see, that matches what our derivative is. The slope is 1500, which it should be because that's the rate of change at 50. So for our last slide, these are your questions getting ready for class. So after you go through the section and you practice the assignments, try to answer these questions the best that you can. And if you can answer them comfortably, you know you've mastered the topics in this lesson.